Yeah, thanks for the opportunity to give a talk in parallel evaluation from home. This is Lu Yin from Shanghai University. Today, I will introduce the topic early dark energy as a unified explanation for cosmic birefringence and hypertension. Here is my cooperators. We have finished 2 papers in this topic. As introduced in this paper, Komatsu has pointed out the CMB observation will introduce the answer of fundamental physics. These new observations include the light bird, the polar bear, and act. And the new physics include the cosmic birefringence and the cosmic inflation. The cosmic birefringence is about the dark matter and dark energy coupling with photons, and the photons' plane of linear polarization will have a rotation. Till now, the observation result for this rotating angle beta already be 0.34 degree, and the confidence is larger than 3.6 sigma. And the cosmic inflation is about in the early universe, the cosmic inflation can produce the stochastic gravitational background in the early universe. So today we will introduce about the cosmic birefringence. That is about the physics from the CMB time to the present observation. The cosmic birefringence is important not only because it's a new phenomenon beyond the lambda CDM, but also it's evidence of parity violation. In traditional, the explanation for the cosmic birefringence is about the axion coupled with the photon when the Chern-Simons term. This G is the Chern-Simons constant, and the theta is the potential of axion field, and the F mu nu tilde is the electromagnetic tensor of the photon. We will give numerical constraints for this constant number G in the next. So the axion can be dark matter or dark energy, which can act as a birefringence material in our universe. With this modification by the Chern-Simons coupling, the F mu nu tilde will provide a parity-odd term. So the equation of motion can be modified in this way. And the different phase velocity of right-hand side and the left-hand side photon polarization will be modified as this. The EB is important because, for example, the EE mode, E mode after symmetry, it is totally the same. And the B mode after symmetry, it have a 45-degree tilting. So the EE mode will be parity even term, and the BB mode will be also parity even term. And the EB mode, the EB correlation will be will be an important parity odd term to consider the parity violation. In general, the rotating angle beta will be definited by the constant term G, a constant number G, and the difference of the potential in the early universe and the present observation. The EB correlation term is also dominated by the difference of EE mode and BB mode, and also depend on the rotating angle beta. And this is a difference of E mode and B mode in present Planck observation, especially when the rotating angle beta B back to zero, the EB correlation will be also totally back to zero. But based on present Planck observation, Planck analyze, the EB power spectrum already have several non-zero peak. So that is the evidence to about the present observation of EB mode. We consider the cosmic birefringence is comes from early dark energy models. The early dark energy model is a pseudo-scalar field, and the potential is given in this form. In the early universe, the particle start slow roll and it will start oscillation in the minimal, around the minimum. This is a moment of it start slow roll and start oscillation. And here is the equation of state of the early dark energy model. During the CMB time, it still have a lot of early dark energy in our universe, and with the evolution of universe, the early dark energy start decay, and at present time it already disappeared back to zero. The early dark energy model already be considered effective model to solve the H0 tension, especially when compared with other candidates to release the H0 tension, especially when n equal to 3 have the best phenomena in several constraints. The early dark energy model already be fitted very well with CMB observation. For example, it fitted well in the CMB TT mode and EE mode. How about the effect in CMB EB mode? Several papers already considered this topic about the early dark energy with potential in order of potential in n equal to 3, and constrains the effect of the early dark energy and power spectrum in the EB mode. In our work, we consider to constrain the Chern-Simons coupling constant term G in early dark energy model, also with n equal to 3. We have two fitting results. One is about the green line. Green line is fit all the parameters, all the early dark energy parameters with TT, TE, EE, especially we added the EB new data from our own analyze. Also include the BAO and supernova data set. The result of GEDE is 0.148, this number. And the orange line is the result have two steps. The first step is get the best fit result of other early dark energy model parameters from the traditional data set. And the second step is using this best fit result and the new EB data set to constrain the GEDE, only fit the GEDE. this result is 0.59 for the number of G. In this way, we can see the result. This is the result of fitting all parameters in early dark energy model and GEDE with the EB new data set. The constraint result is H0 equal to 72.03. Compare with this value is higher than the traditional result. This is the traditional early dark energy. This is the standard early dark energy fitting result. Without consider the cosmic birefringence effect. And in this way, the G is the same with our previous blue line. Then we zoom in to see the distribution of these parameters. We can see in our fitting result, we have a higher value of FEDE. That means the new EB data set prefer more early dark energy in the recombination time. For this reason, it have better result to release the H0 tension. Yeah, this value is several times higher than the traditional early dark energy models result. F is much higher. We also consider to compare the effect in different dark energy models in early universe, include the early dark energy model, rock and roll model, and alpha attractor models. We just want to see in the CMB EE power spectrum, this model has some difference in the low L part, but very hard to be distinguished in high L parts. But if we consider the different early dark energy models in the EB mode, it can be distinguished very effectively. So the EB power spectrum is an important smoking gun to distinguish different early dark energy models beyond the EE spectrum. We also get the constraint result of rotating angle beta from different models. The early dark energy model constraint result is the rotating angle beta is 0.34 degree, but in alpha attractor and rock and roll model, the rotating angle is much more smaller. So this is the conclusion. The cosmic birefringence is a remarkable parity violating effect, which is beyond the standard cosmic prediction. The rotating angle beta at present is 0.34 degree. And the EB data set can help to release the H0 tension in early dark energy model. The EB power spectrum cannot distinguish this model at present observation, but in the future, it will be very helpful to distinguish the different early dark energy models, especially is more effective than present EE power spectrum. That's all I want to introduce. Thank you very much.